Hi, everyone. Having spent the last few weeks looking at derivatives of multivariable functions, we now want to turn our attention to integration. Unlike in the single variable case, where we really only developed one notion of the integral, the Riemann integral, for vector and scalar fields, we will have multiple notions of integration. Today, we want to begin by looking at one type of integral called a line integral. Before we can formally define the line integral, however, we will need to spend a few moments defining some terms and discussing different types of functions in Rn. So to begin, I want to first define a path. Now, on one level, a path is exactly what you think it is. So if we're in R3, right, a path is just some curve moving through R3. But as we'll see and discuss, this in fact doesn't uniquely define a path. So we need to be a little careful in how we define and discuss all these things. So let J be the closed interval AB, and we're considering this here to be a finite interval. So A and B are real numbers with A less than B. So this is a closed interval in R. And then I want to define a function alpha from J into Rn, which is continuous on J, and that is going to be what I'm going to call a continuous path in Rn. Additionally, I'll say that the path is smooth if the derivative alpha prime exists and is continuous on the open interval AB. So here, one way to think of this is to think of this interval J as giving you some time interval. So I can imagine maybe that my curve starts at alpha of A. Sorry, and A is a scalar quantity. I put the arrow over the wrong thing here. So alpha of A, right, is a vector. And if we write that in sort of the standard position, right, really it's this vector coming from the origin. And what we do is we look at what happens to the tip of that vector, right, as this value t goes from A to B. So at some other time, the vector may be pointing here, then pointing here, and then eventually it's pointing over here, and maybe this would be alpha of B. Okay, so what I have drawn here is a path, a continuous path. Okay, it starts at alpha of A, it ends at alpha of B. As you can see, I mean, just from looking at this path, it seems nice and continuous, but this is a path in Rn. Again, now what we have visualized here is the graph of the path. It's all the points that the path hits. But notice that it's entirely possible, if I sort of imagine that my finger is tracing along the tip of this vector as it changes, it could come this way and then turn around for a little bit and go the other way. It could come back and turn back. So I could sort of retrace parts of this path several times, potentially. That would still give me the same graph of the path, although it would lead me to a different function alpha. Okay. So we have to be a little bit careful in sometimes being clear about whether we're talking about the graph of the path or whether we are talking about the actual path itself. Now, one way we distinguish that, because the word path often gets bundled up to mean the graph of the path, right? And that sort of makes sense. And the common usage of the word path in English, right? You're usually just thinking about the actual like trajectory here, right? The actual graph. So we often talk about parameterizations, right? So you could have two different parameterizations of this path that trace out the same graph, right? But I really have different parameterizations. Okay. So again, all of this, we'll be exploring all of this and how all of this affects line integrals, which we'll define momentarily. But again, the first thing we need is some notion of what a path is. Now, I want to extend this even a little bit further, okay? So I've defined, so a path, my function alpha just needs to be continuous. So that's a continuous path. A smooth path, right? So just flipping back over here momentarily. A smooth path just means I need the derivative alpha prime to exist and be continuous. And now I want to define a piecewise smooth path. So a path is piecewise smooth if you can break it up into a finite number of pieces such that each piece is smooth. Okay, so you can imagine, for example, and I'm not going to draw axes again here. You can either imagine this in the plane or in all of our three, either way. But you can imagine, like if I have a path here, let's say it's just in the plane. Okay, and so right, maybe my path sort of looks like this. Okay. So if I think about this path, well, it's not going to be smooth at the places you expect, right? So where I have a corner, for example, um, here it looks like maybe both of these are differentiable, but the derivatives don't match up again. So I have sort of another corner here, another corner or cusp sort of thing here. So this cannot be smooth because my derivative vector is not going to be defined at each of these 3 points. So this entire path alpha is not smooth. However, I could break it up, if this point is alpha of A and this point is alpha of B, then if I figure out, maybe I call this alpha of T1, alpha of T2, alpha of T3, then between A and T1, my path is smooth. Between T1 and T2, my path is smooth. Between T2 and T3, my path is smooth. Between T3 and B, my path is smooth. So it's smooth on each of these sub-intervals, even though it's not smooth on the entire interval AB. Now, the reason we're taking time to define this is we're going to write down several theorems, and we don't actually need our paths to be smooth. We just need them to be piecewise smooth. We can break them into a finite number of pieces, each of which is smooth, then that will be sufficient to prove many of the theorems that we'll want to prove. All right. So now that we have defined all of this, okay, we want to look at our main definition for this video. So our goal is going to be to define the line integral, understand why it's defined in the way that it is, and then to work through an example to really start to understand what line integrals are and what sort of properties we might expect them to have. So let's define the line integral first of a vector field. So let f be a vector field defined on the graph of a piecewise smooth path alpha. Okay. Then the line integral of f along alpha. So we denote the line integral of f along alpha as the integral of f d alpha. Okay. Sometimes with or without this alpha down here. Okay. Sometimes it's there, sometimes it's not. We'll actually see in a minute there are many notations for line integrals, so this is just one. But this is just the notation for the line integral of f along alpha, and it is defined to be, now this is just the Riemann integral, so this is the Riemann integral from a to b of f of alpha of t inner product with alpha prime of t dt. Okay. So notice, right, alpha of t is a vector in Rn. F is a vector field, and it is defined on the graph of this path. So f of alpha of t is defined, and f is a vector field in Rn. So f is from Rn to Rn. Okay, so this is a vector in Rn, inner product with a vector in Rn. That gives me a scalar function. And so I'm just defining this line integral to be the integral of some scalar function. So this thing on the right-hand side, it's just a normal integral. Okay, we're defining the line integral in terms of this regular integral that depends on both the vector field and the path alpha. Okay, but why? Like, what is this capturing, right? We could write this down, we could prove all sorts of things, but you have to imagine that there must have been some reason for defining this. So you can imagine again that we're just in the plane and we have some path alpha. Okay, so here's alpha, okay, alpha of A, alpha of B, okay. And I also have a vector field that at the very least is defined at each point along this path, okay. So I could just say start drawing some points or some of the vectors along here. So maybe There's a vector. Right now, these vectors, they don't have to point in the direction that alpha is moving, right? They could point any which way, right? So over here, maybe it might point back this way. Here it might point like this. Okay. But at each point along here, there is some vector f of alpha of t, right? So this is, and we'll use this one for sort of illustrative purposes. So this is f of alpha of t. Okay. Now, the goal of the line integral, or one purpose it serves really, is usually to help calculate the amount of work that is done by some vector field as a particle moves along a path. Okay. So one way to think about this is, okay, if I want to do that, well, that's a scalar quantity I want to capture. And at each point, yes, this vector is pointing this way, but the particle or whatever's moving along this path is not moving in that direction. So not every bit of the vector field that's being applied to whatever's moving along this path is in a productive direction. So what I really want to measure is the component of this vector that's moving in the same direction as alpha. Okay. So in order to do that, what I want to understand is, okay, I need to first define something that's in the direction of that alpha is moving. Well, that would just be the derivative. Okay. So alpha prime of t is tangent to the curve there. Okay. But again, I don't know what magnitude that vector may have. That's going to depend on how fast the particle is moving, right? And what I really just want to understand is I want to understand how much of this, think of this like a force, how much of this force is being applied in this direction. So what I really want to understand is I want to understand what is the component of f of alpha of t that's in the direction of alpha prime of t. Well, back in Calc 3, you would have derived a formula for the component of a vector u in the direction of another vector v. So this is really just a formula. I'm not going to belabor it too much. This component is f of alpha of t dotted with alpha prime of t divided by the norm of alpha prime of t. That is the component of f of a that's in the direction, or sorry, of f of alpha of t that's in the direction of alpha prime of t. All right. So you see this dot product here and this dot product here, but how do we get then from here to here? Well, okay, at each point, I can define this quantity, right? And this is a scalar quantity at each point. And now I want to add them up, but I have to make a decision, which is sort of how do I want to weight each of these values? I could weight, one way to weight them would be to weight them with respect to like the time, like how long I'm spending at each of these points. Right now, technically, I'm not really probably spending any time at each of these points, but right, do I want to sort of weight it with respect to time, or do I want to weight it with respect to arc length? So to help you sort of see the difference, right, you can imagine if I just have some small curve here, right, if I weight these with respect to arc length, each of these should roughly receive the same weight, right, each of these subintervals. If I weight it with respect to time, though, and let's say I move really fast along this and not very fast along this, so I spend very little time here, spend a lot of time here, right? Then these aren't going to be weighted equally anymore. Okay. So what the choice we make for line integrals, and again, this is really comes from wanting to understand things about physics, right? Is I'm going to choose to weight this with respect to the change in alpha. Okay. So I want to multiply this. I want to weight each of these with sort of respect to how long that applies, right? So you can imagine taking equally spaced with respect to the arc length partitions of this, right? And that's going to give you your delta alpha. Well, that's great, but that's hard to integrate with respect to because I don't have a variable that gives me that. My variable gives me time. So then, and again, this takes some derivation, but you can essentially apply the mean value theorem and say, well, if this is differentiable and I have alpha as a function of t, then this is really equal to, sorry, that's not a derivative there, f of alpha of t divided with alpha prime of t divided by norm of alpha prime of t. Okay. But then this should be equal to the norm of the derivative times the change in time. So norm of alpha prime of t times delta t. And again, that really is coming from a mean value theorem type argument. Well, then you look at this and go, that takes care of that. So this is really f of alpha of t inner product with alpha prime of t times delta t, right? And now I want to add all those up and take a limit as that delta t goes to 0. So that just then becomes the integral here of this quantity. Okay. So again, this is not, well, this is a definition, so it doesn't require any proof. This is just sort of trying to give you some motivation for where this is coming from and what this is trying to capture. It's trying to capture the component, the total components of the vector field that are in the direction of the curve weighted with respect to arc length. Okay, that's really what this quantity is trying to get after. Okay. Now that we've done that, I think it's time to work through a couple of examples. And in fact, what I want to do is I'm going to pick one vector field, and we're going to take a few different paths and calculate the line integral of that one vector field along 3 different paths. Part of the reason we're going to do that is that's going to help us start to understand how these line integrals depend or don't depend on different paths or parameterizations. All right. Sorry, before we do that, I did just want to mention this notation is common, but there are lots of other common notations, okay? So sometimes folks will use C and R, where R, this helps sort of distinguish between the curve C, that's sort of the graph, and R, which is the parameterization of that curve. So this notation has the advantage that it sort of helps distinguish there. These next two, they're really this version is a special case of this version. And the idea here is we're just going to break out this. If I think of this as an inner product, if f has components f1, f2, f3, all the way up to fn, then we could write this as the integral f1 dx1 plus f2 dx2, so on and so on and so on. In the special case that we're in R3, sometimes we might call the components of that vector field P, Q, and R. And then we will just write that as the line integral over the curve C, P dx plus Q dy plus R dz. Okay. Again, these are all just different notations for expressing line integrals. There's no difference in how the line integral is defined. These are just different notations. And again, they have different advantages and disadvantages depending on particular context. All right, so now to the example. Okay, so we're going to work this entire time with the same vector field. And I have intentionally here used some slightly different notation just to get us used to seeing things in different notations. So let f of xy, so this is a vector field, it's going to be equal to the square root of y times I plus x cubed plus y j. Now remember that I and j, these are the standard basis vectors in the x and y direction. Okay, so one way you could make sense of this is you could actually just start writing this out. So this is like square root of y 1, 0, or let me actually write these as row vectors. That's what the book tends to do. So 1, 0 plus x cubed plus y, 0, 1. Again, this is a scalar, this is a vector, scalar, vector. Okay, so this ends up being just square root of y in the first component. So square root of y times 1 plus x cubed plus y times 0. In the second component, I just get x cubed plus y. Okay. So really, all this notation is doing is giving you the x component and the y component. We could write it as a vector in this way. Okay. And here, I'm going to use, in each part of the example, I'm going to use a different path. So I'm going to call this first one alpha 1. And my goal for all of these is simply going to be to calculate the line integral of f with respect to that path. So the line integral of f, in this case, the alpha 1. Okay. All right, well, by definition, this is the integral from a to b. So here, my parameterization goes from 0 to 1. Okay. Of what? Of f of alpha of t dotted with alpha prime of t dt. All right, let's go off and figure out what this is, then we'll come back and actually finish. Now, like once we figure out what this is, then this is just a standard, Calc 1 or Calc 2 integral type problem. All right, so let's see if we can figure out what that is. So first thing I need is I'm going to need f of alpha of t. So what does that mean? F is a function of two variables, and alpha is a vector value function. So it has x and y outputs. Okay. So, I'm sorry, these should be alpha 1s. And this should be an alpha 1. All right. So, what is f of alpha 1 of t? Well, alpha 1, let's first just understand what it is doing. So it is, if I come over here in the plane, okay, when t is 0, this gives me back the vector 0, 0. Okay. When t is 1, this gives me back 1, 1. Okay. And if we notice here, we have basically our x component is equal to t and our y component is equal to t. So our x and our y components are always equal to each other. That means we're moving along the line y is equal to x. Okay. And in fact, right, this path, alpha 1 of t, it's just moving at a uniform speed linearly between 0, 0 and 1, 1. Okay, that's all alpha 1 of t is doing. All right. So now if I want to evaluate f of alpha 1 of t, that means my x component is just t and my y component is just t. Okay. So everywhere I see x, I'm going to plug in t, and everywhere I see y, I'm going to plug in t. So this becomes, and I'm just going to write this in its usual vector form. So this becomes square root of t, comma, t cubed plus t. All right, that's f of alpha 1 of t. I also need alpha 1 prime of t. Okay. Well, to take the derivative of a vector valued function of a scalar, I just take the derivative of each component. So that's just derivative of the first component with respect to t is 1, derivative of the second component with respect to t is 1. All right, so there's f of alpha 1 of t. Here's alpha 1 prime of t. Now I need to take their inner product. I just multiply the corresponding entries together and then add each of those products. So, and that's going to be the thing I want to integrate. So this becomes the integral from 0 to 1 of, now this inner product here, right? So I get square root of t times 1 plus t cubed plus t times 1. Just get that dt. All right. Now this is just a standard Riemann integral. So let's see here. This ought to be the antiderivative. This is t to the 1/2. So the antiderivative will be 2/3 t to the 3/2. plus the antiderivative here will be t to the fourth over 4. Antiderivative here will be t squared over 2. And we're going to take all of this, evaluate at 1 and 0, and take a difference. Well, of course, when you evaluate all these at 0, you just get 0. So we're just left here with 2/3 plus 1/4 plus 1/2, which, if you do a little bit of arithmetic, gives you 17/12. Okay. So there's a nice first standard, simple example. We get 17/12. Okay. Now the question we want to ask is, well, what if I switch to a different path? Okay. Now, in order to do this, right, certainly some of our work is going to change. Okay. So before I even change the path, let's just think about like what's going to change. I mean, yes, okay, the name is going to change, right? I'm going to shockingly call this alpha 2. Okay. So this dot product in here, this inner product will change. Okay, and so then all the rest of this stuff is going to change. Also, maybe 0, 1 is going to change depending on how I parameterize this path. So we'll have to see what happens there. Okay. And of course, these things over here, I'm going to still need to calculate both of them, but now they're going to be with alpha 2s and they'll be different things. Okay. So all these things are going to change. All right. All right. So let's look at what are we going to use for alpha 2 then when we go to switch this. So now that we've changed alpha 2, let's look and see what actually is going to happen here. So now I have alpha 2 is equal to t squared I plus t cubed j. Now, first, let's just think about it in terms of what's the graph of this path going to look like. So here for alpha 2, I really have my x component is t squared. My y component is t cubed. If I want to understand the graph, I want to understand how does each of these variables' relationship to t give me some relationship between x and y. So what I can often do is just solve this for t. So this gives me that t is equal to the square root of x. Technically, I should put plus or minus the square root, but notice here I'm only looking at t's between 0 and 1, so they're always positive. Okay, and then once I do that, now I can substitute in for t here, square root of x, so I'll get y is square root of x cubed, or equivalently, it's x to the 3/2. Okay, so the graph of this path ends up looking something like this. Okay. Now notice these paths start and end at the same points. They both start at 0, 0. They both end at 1, 1. But they carve out different trajectories, right? The graphs are different of these. So let's see what happens here then if we switch to alpha 2. All alpha 2. Okay. And then I come down here and say, okay, I need f of alpha 2 plus alpha 2 and alpha 2 prime. All right, so what's f of alpha 2? So I come up here. Now my x is t squared. So everywhere I see x, I'm going to put t squared. Everywhere I see y, I'm going to put t cubed. So this is t cubed goes into y, so this becomes t cubed square root. So square root of t cubed, which is the same as t to the 3/2, comma. Now here, I'm going to get t squared cubed. That's going to be t to the 6th plus y, which is t cubed. So plus t cubed. All right. And then I need my alpha prime of t. So derivative of the first component is 2t. Derivative of the second component is 3t squared. And now I need the inner product. So I'm going to get a t to the 3/2 times 2t. That's going to give me a 2t to the 5/2. Then I'm going to get 3t squared times t to the 6 plus t cubed. That's going to give me a 3t to the 8 plus a 3t to the fifth. Yeah. And now, of course, I'm back to this, just the integral of a scalar function, right? So antiderivative, let's see, that'll be to the 7/2. So this will be 4/7 times t to the 7/2 plus it'll be 1/3 t to the 9th plus 1/2 t to the 6th. That's the antiderivative. Evaluate at 1, 0, and take a difference. At 0, all of these are 0. At 1, each of the variable pieces just becomes 1. So I get 4/7 plus 1/3 plus 1/2, which a little arithmetic will give us is 59 40-seconds. All right, so again, it's just calculating another example. Now here, let me sort of point something out here. We're going along a different path. So, and that path is not just a different path, it's a path that gives me a totally different graph. So maybe you're not surprised that we get a different value. However, I do want to sort of think about one thing, which is that for a lot of functions, when we were just in the scalar case, like Calc 1, Math 5610, if we could find an antiderivative of a function, then its integral only depended on the value of that function at the endpoints, and these have the same endpoints. Okay, so it almost feels like these should be equal, but they're not. Okay, we'll talk about in a little bit why that isn't the case. But like again, it's taking a different path, it's a different sort of thing, so it's probably okay. But I sort of feel like integrals should mostly just depend on the values at the endpoints, the values of the antiderivative at the endpoints. Okay? But clearly that's not exactly the case here. All right, now we're going to switch to an alpha 3. Okay, now for this, I am not going to write out all of the work. By now you've seen 2 examples. I think you should be able to do most of this work. So what I'm going to do is I'm going to flip over and change the alpha 3. I'm going to start erasing. You'll probably need more time than it will take me to erase. So you may want to pause the video, but I want you to work out what it is, what this line integral is when we change to this alpha 3. Now, I'm going to momentarily just write up the answer, and we'll sort of talk about that. But take a moment, pause it, see if you can calculate this one on your own. It'll be a good little practice run getting back into calculating some of these things if it's been a while since you took Calc 3. All right. So if we go through this process and we write out the line integral of f along alpha 3, we get 59 40-seconds. Now, maybe you're looking at this and going, Quinn, I think you made a mistake. That was the answer to the last problem. No, I didn't make a mistake. This gives you the same answer. Now, as soon as you get the same answer, you should probably think that's weird. Okay, I wonder why that happened. Well, let's think about this curve, this path alpha 3. Alpha 3 looks like, so let's see, we have x is equal to t, and y is equal to t to the 3/2. So really here we have y is equal to x to the 3/2, which notice that gives me that alpha 3 has the same graph as alpha 2. Okay. Now again, while technically they're not the same path because the functions are different, we would often say these are the same path with different parameterizations. So what's happening here is we're moving along the same path here for alpha 3, but we're not, like, if you started both of them at t is equal to 0, what you would see is that your points aren't actually at the same point at the same time, right? So they're not exactly the same. You're not moving along that path in the same way, but you're eventually traveling along the same graph in the plane. Okay. Now, what we're starting to see here is, it looks like if you're moving along the same path, you might get the same line integral. And the answer to that is it turns out, well, again, maybe. But we need to think a little bit more about why that might be the case. So what I want to do is I want to conclude this video by really addressing a couple of these questions that have come up about this. And these questions will guide the next couple of videos as we start to prove some important properties of line integrals. So to sort of finish up and to summarize here, right? I think there are two reasonable questions we might want to ask about line integrals. And the first is raised by alpha 2 versus alpha 3, which is, are line integrals independent of parameterization? So there we saw that alpha 2 and alpha 3 have the same graph. They're just different parameterizations of that curve. And so maybe line integrals are independent of parameterizations. And the answer to this is really yes, they are independent of parameterization, but we sort of have to define what we mean for two parameterizations to be equivalent to one another. So in the next video, we'll define what we mean for two parameterizations to be equivalent. And then we'll say, well, if you have equivalent parameterizations, then they give you the same line integral up to possibly a sign, because the direction that you traverse that curve could make a difference. Okay, so the answer to this is more or less yes. We just have to be careful about how we define some things. Now, the second question is one that we raised is sort of, are the line integrals independent of the particular path, but maybe only dependent on the endpoints? Now, in general, we know that the answer to this must be no, because alpha 1 and alpha 2, or alpha 1 and alpha 3, they both start and end at the same points in the plane, but they take different paths between those points. So in general, the answer must be no. But again, this seems a little strange when I consider the fact that, like in Calc 1 or Calc 2, right, we wrote down something like this. And this was the fundamental theorem of calculus. Okay. And one way to interpret this is that the value of this integral, now it's a different type of integral. It's the Riemann integral. It's not a line integral. But the line integral is defined as a Riemann integral. So it sort of feels like, you know, here what we're saying is that the value of the integral really only depends on the value of this other thing at the endpoints. And if you don't change the endpoints, right, then there's nothing about a path here. Okay, so what's going on? Well, what I want you to think about is that one of the conditions here, right, that you never really run into in practice because you're only ever doing this in a calculus book where everything's set up to work. But the condition here is that f must have an antiderivative. Okay, capital F has to be the antiderivative of little f. Well, if we think about trying to write something like this down for line integrals, right, this would need to say something about some sort of antiderivative of the vector field f. Well, what does it mean for a vector field to have an antiderivative? It turns out that we will come up with something like a fundamental theorem if we have an antiderivative of f. What that really means is we need a function whose gradient is this vector field f. Okay, so we will see that in some cases, line integrals are independent of path, and that will be precisely when this thing has some sort of appropriate antiderivative. However, in many cases, we'll also see that this doesn't have any sort of appropriate antiderivative, and therefore line integrals will depend on the path that we take. So the answer to the first part will be pretty much a resounding yes, that line integrals are independent of parameterization. We'll see that in the next video. And then the question of whether or not line integrals are independent of path really depends on whether this has an antiderivative or not. And so we'll look at establishing that and conditions under which this has an appropriate antiderivative in future videos.